Well, good evening, everyone. Michael Comer here, Marketing Manager for McGraw-Hill Education here in Columbus, Ohio. I want to welcome you this evening to the fourth of a series of webinars on the Common Core standards for mathematical practice. These standards are new, and their language can make them seem complicated and a bit intimidating. Our goal here at McGraw-Hill is to help you make sense of these new standards. Our objectives tonight are to first to help familiarize yourself with the two mathematical practice standards from the Common Core, and second, we want to show you how you can incorporate those mathematical practice standards into your daily lessons. And on a third note, we'd like you to take a look at how these standards are addressed within the new McGraw-Hill MyMath program. As we are all probably familiar, the Common Core State Standards are a set of research-based mathematics standards that span from kindergarten through high school. These standards are closely aligned to the college entrance requirements and career expectations for the 21st century. And these standards include rigorous content with a focus on computational fluency in the early grades and instilling higher order thinking skills in students as they progress across the grades and as they mature as learners. The Common Core State Standards are divided into two types of standards. There are the content standards and then the practice standards. The content standards are organized by grade levels for grades K through 8 and for concepts across high school. There are also the 8 practice standards that apply across all grades K through 12 and are based on the process standards from NCTM and include the strands of mathematical proficiency from the National Research Council's report, Adding It Up. They include the broad goals or habits, such as working towards accuracy, using abstract reasoning, modeling, etc. The mathematical practice standards are intended to be interwoven with the content standards. If you want to think of it as the content standards are the what of the curriculum, then the mathematical practice standards are the how and the why. This series of workshops that McGraw-Hill is sponsoring will focus on the standards of mathematical practice as they particularly apply to the K-8 classroom. So let me review for you for a moment how we've organized these 8 practice standards into this 4-workshop series. As we look at the practice standards, there are some inherent relationships among them that allow them to be organized in a way that might make them easier to think about. And we have already completed 3 of the webinar series. They are available to you if you wish to go back and preview them, or if you happen to miss them over the last several months. You may visit mheonline.com/mhexchange, and there you will find these pre-recorded webinars. The 8 mathematical practice standards weave throughout the content standards. We looked at the mathematical communication skills, which really center around standards 2, reason abstractly and quantitatively, and number 3, which are constructing viable arguments and critiquing the reasoning of others. Standards 4 and 5 we've labeled as the mathematical mechanics, since these standards address the mechanics of working with models and tools to solve problems. They are the skills that students must develop in order to make good decisions about which resources and ways to make their calculations more efficient. Standards 7 and 8 address those higher order thinking or critical thinking skills, where students must apply them in order to go beyond the simple computation in order to really understand how mathematics works. And finally, there are those standards that we'll address tonight, standards 1 and 6, which are those overall habits of mind, the skills that students need that they need to learn early and use regularly in order to successfully apply to all their other skills. But before we begin, what I'd like to do is just get a sense from you and ask for a poll to find out where you are from. So I'm going to open up a poll question tonight. Where are you from? And you'll see it on the screen. If you could participate and identify whether you're from the East, the Southeast, the Midwest, the Mountain region, or the West Coast. And I'll take a few minutes to give you a chance to log in. All right, thank you. As we see, as we share the poll results, you'll see that the about 2/3 of you are from the East, and 1/3 of you are from where I am, out in the Midwest. The other thing I'd just like to do is find out from you also, what students or grades do you cover? So you'll see on the screen whether it's elementary, middle school, high school, whether you're a supervisor or a math coach, or you have some other position. Again, if you just take a minute and use the polls to vote. All right, let me close the poll and then share what the results are. I can see that approximately 80% of you are elementary tonight. Well, what I will try to do is gear my comments and examples to the elementary level, but I want to make sure that I include, for those that are both high school and other, some opportunities to think about how you might apply these standards within your classroom. Thank you for sharing that at the moment. So as we begin, I just want to go back and review for a moment what we consider to be a mathematical practice. And that is, a mathematical practice may be thought of as the goal or outcome that students will achieve as they strive forward in their work. It is the habits of mind that they create. It is a way of thinking and doing that would percolate through their mind as they work to solve problems. Not only in mathematics, but really in a broader sense through all problem solving that they would encounter in their daily lives. It includes thinking, speaking, reading, and writing in mathematics. It includes approaching problems using logic and reasoning as they work to solve issues or identify problems that are unfamiliar to them. It also includes using a degree of precision in the details of those solving of problems, and it includes attending to the details of the math, while at the same time keeping the bigger picture in mind. And lastly, it includes having the flexibility of multiple strategies at their command, allowing a student to evaluate a problem and to pick a strategy that they feel best will work, but then also to change strategies if they find that they run into problems. Overall, the mathematical practices are really the good habits of mind that we want all students to be a part of or to be embedded in their work. And they should be embedded within the classroom practices. So the bigger question that we have found ourselves being asked by teachers across the country is, how do we do mathematical practice? And so what I'd like to say is, in the mathematical practices are not a checklist of discrete skills, but are really a collective result of what we create in students as a sense of a positive attitude and a positive disposition towards learning and applying the mathematics they know to their daily lives. And it can be accomplished in some of the following ways. One is that incorporating problem-solving routines embedded in ongoing classroom discussions. It is about fostering a classroom culture where learning encourages discourse and discussion, and that providing an opportunity where the mathematical tasks vary in both their difficulty, their context, and their complexity. In other words, what I'm saying is that mathematical practices are not done in a 15-minute learning block or in some small group activity placed in the center, but it is truly fostered by the teacher who models a constructive approach by using out-loud thinking, and who might nurture in the students the process of both visually and verbally solving problems so that their students can both see and hear and understand the internal workings of the mind as it works to decode and unlock a problem in order to find a solution. So let's see if we can begin with an example tonight. And I'm going to ask you to use the chat in a moment to share with us what you have or what your thoughts are. Here's a problem. It's a kind of multi-step logic problem that children might encounter. Anne, Lila, and Ilium like red, pink, and purple, and daisies, roses, and irises. Anne does not like pink, purple, or roses, and Lila loves daisies, but not pink. Can you list each person's favorite color and flower? So what I'd like you to do is take a moment and think about how you would go about solving this kind of problem. And then if you'd like to use the chat box and just send me a message about what the strategy or process you'd use in order to solve the problem. And then we'll move on to sharing. Okay, now don't be shy to share a strategy. What might you use to solve this kind of multi-step problem? All right, okay. One way is to create a grid or a matrix. One way, a process of elimination, okay. Oh, yeah, well, not sure how to go about solving it. All right, well, let's share for a minute and see what we have. In this particular example, let's see what we know, all right? One way to solve maybe, as somebody just mentioned, was to use a grid or a matrix in which to kind of sort the different kinds of information that you are, or criteria that you know. We know that we have 3 girls, Anne, Lila, and Ilium. And we know from the problem that there are 3 choices of flowers and 3 choices of colors. And we know that each of the girls has the same 3 choices of flowers and 3 choices of colors. But the question is, what else do we know? Well, for example, we know from reading the problem that Anne does not like pink, so we can place an X on the pink. We know that she does not like purple, so we may cross an X on the purple. And that we know that she does not like roses, and we can put an X on that. What else do we know? Well, we also know that Lila loves daisies, but not pink. So we might put a circle around the daisies, knowing that that's what Lila likes. And at the same time, we can then X out pink. So as we look at the problem from the chart, we can see that there are several opportunities now where our thought process may lead us to doing different steps. And I'd encourage them, the children, as we work through the practice of persevering and solving the problem, is to talk about what they see in the problem and how they might move forward next. So in this particular case, from the chart we can see that only one person could possibly like pink because that's the last left. So if we find out, as we look at the example, that what we want to know is the person's favorite color and flower, and we see that one person could only like pink, and that would be Ilium, because the other 2 choices are blocked out. What also do we know by looking at the chart? Well, we know that Anne must like red because that's the only choice left for her. And as we look further at the chart, we can see that if Lila likes the daisy, then Anne and Ilium can't like that at the same time. So we can put an X on those spots. So do you see how using a chart provides an opportunity to move the students forward in persevering through a problem that seems complex and unsure of how to solve? that this works them into the opportunity to move it forward. So as we use the pictures and we use the chart, we might then say, well, what's the next logic? Well, if Anne doesn't like the daisies or the roses, she must like the iris. And then neither of the other two girls can like the iris, so we could X those out. And as we continue with the logic, we can see that the logic implies that if Anne likes red, then neither of the other two girls can like red. And as the chart helps us to sort the information, we recognize that the chart then becomes a tool. And as we think of this kind of problem, this is a fourth grade problem presented from a problem of the day. So it gives students the opportunity to begin to think about how they can organize and strategize around solving the problem. So as we work through the rest of the problem, we can see that then Anne likes irises in red, that Lila likes daisies in purple, and that must mean that Ilium likes roses and pink. What we'd like to do tonight is think about the two standards that are about the habits, the perseverance, what we wish to instill in students, and that is to make sense of problems and persevere in solving them. So think for a minute of the problem of the girls and the flowers and the colors. In this problem, did you immediately know the answer? Probably not. It takes some time to assimilate what the question is asking, what information I'm given, and then to think about how I might go about solving the problem. And a good problem is exactly that, something that takes a few minutes to think about, to reflect on, and then move forward. It's not an exercise, but it is truly a problem. How did walking through the problem exemplify standard of mathematical practice number 1 about making sense of the problem? That's right, by walking them through, by breaking the problem down, by either making a list or a chart or drawing a picture is a way to help the students then begin to make sense of the problem and persevere in solving it. Standard 6, as we're going to look at tonight also, looks at the importance of the details, the specificity and the clarity that make mathematics an understandable language. While none of the mathematical practice standards stand alone from the rest of their sisters, these two standards together speak to the practical importance of thought and focus in mathematics. And as we work through a couple of other examples tonight, what you'll notice is, now that we're at the end of the series, is that it's very difficult to tease out one particular practice standard over another, that they are intertwined like fingers joining hands. The idea as we work on this is to focus on not all of the practice standards in each problem, but to perhaps identify one or two we wish to focus on and attend to with a more focused and purposeful attention to help students begin to make sense of how they can use it in solving problems on their own. So the girls keep popping up wherever we look. So let's go back now and think about practice number 1, about making sense of problems and persevering in solving them. Is that students start by explaining to themselves the meaning of a problem. They have to look for entry points to the solution. They need to analyze what's given, what are the constraints, the relationships, and the goals of the problem. They may make conjectures about what form or meaning the solution may have. And then they plan a pathway. Students don't jump into solving using or finding a solution attempt, but they take a moment to think about what their path of instruction or what their path to the solution will be. Now, in order to do that, they must consider similar problems or analogous kinds of problems. In other words, they have to ask themselves, have I seen this before? And then try to make special cases in simpler forms of the original problem in order to gain an insight into its solution. The problem with the girls is a good example that once we model the process of having these multi-step or grid-like logic kinds of problems, once we begin to develop a pattern, it's easy for students to begin to understand how I might use that same strategy again and again in similar problems. And as students work, they must monitor and evaluate their progress and change course if necessary. Older students might, depending on the context of the problem, transform algebraic expressions or change the viewing window of their graphing calculator to get information they might need. The mathematically proficient students can explain the correspondences between equations, verbal descriptions, tables, graphs, and to draw diagrams of important features and relationships. They can graph the data and then search for the regularity or the trends, while younger students might rely on more concrete objects or manipulatives or pictures as a way to help them to conceptualize and solve the problem. Either way, mathematically proficient students check their answers to the problems by using a different method, and they continually ask themselves, does this make sense? But what does it mean for your students? It means that they must need to really think about the problem before they jump into that solution. And some of the questions that we recommend asking students as they work through this particular mental exercise is to stop for a minute to consider, what is it they know, what do they want to know, and what do they need to figure out in order to find the solution. Might using models or concrete objects help me to plan a strategy? Might I consider what other strategies might work for this particular problem? And then even if the strategy isn't the best one, perhaps students take the time to ask themselves as they work through it, does this make sense? Or is this making sense as I work through the problem? So think about for a moment your classroom experiences. For those of you in the classroom, think about the students that you deal with, and how does this standard relate to the instruction that you provide in the classroom? Do you talk about problems in terms of what is known? Do you demonstrate for students the ways to organize and order the information within the problem? Do you model for them perhaps the reasonableness and stop and ask yourselves, does this make sense? And it is important to select an effective solution strategy to give students an opportunity to analyze what works and what doesn't work as they arrive towards the correct solution. I'm going to show a little video from a grade 4 classroom in which the teacher begins to guide the students in looking for the important information in the problem. In this particular case, the teacher is setting the students up by helping to model through or guide the students through the solution process. So take a moment to listen to this example from a 4th grade classroom.
Follow along as I read the problem to you, and then we're going to go through and we're going to circle the important information in our problem. Anne's class bought 4 boxes of peaches at the orchard. There are 128 peaches in all. Each box has the same number of peaches. How many are in each box? So, give me one bit of important information out of that word problem that we need to know. Okay, Brandon, what's one important information we need?
Anne's class got 4 boxes of peaches.
Excellent. What we need to do is take our pencil now, circle 4 boxes. That's an important piece of information. So everybody should have circled 4 boxes. Good. What's another piece of information that we need to have, Ariana?
There are 128 peaches in all.
Okay, circle 128 peaches in all. what does that word in all mean? What does it mean, Carol?
Altogether.
Altogether. So the total. So our total is 128. Refresh my memory again. How many boxes do we have? Yes?
4 boxes.
4 boxes. Any other piece of information that's really important in this problem? Mustafa.
She has got 128 peaches.
Okay, good. There's 128 peaches total. There's one more bit of information that's really important. Okay, go ahead, Jeff.
And class got 4 boxes.
Okay, we've circled 4 boxes and we've already circled 128. Something different. Dominique.
Each box has the same number of peaches.
Exactly. Underline each box has the same number of peaches. Okay, so now we can actually go to problem number 1 in our book where it says understand. What facts do you know? There are blank peaches divided evenly into blank boxes. Krista?
There are 120 peaches divided evenly into 4 boxes.
Excellent. So there are 128 peaches divided evenly into 4 boxes. So make sure you have 128 and 4 on those lines. Next question is, what do you need to find out? Miles.
We need to find out how many peaches can be put into each box.
Okay, so on that line it says find out the number of, and what you're writing is peaches in each box. Peaches in.
So as we look at this example, think through what did the students do to identify the important information? What were the strategies or the techniques that the teacher was using to help them identify that important information? Circle, underline. All right, good, so that they identify what's needed. And then how did the teacher encourage the students to check the reasonableness of their work? You have to go back to look at the information to make sense of it. Well, what I'd like to do is just show you a few quick examples of how this practice is embedded in the grades K, 3, 4, and 5 of the McGraw-Hill MyMath. And notice the interconnectivity, I had trouble with that word tonight, of the standards. In this particular activity, the students have to analyze the information they know, in which they're going to draw objects, 10 objects in the 10 frame. They're going to color those objects red. And then in the other frame, they're going to draw that number of objects, 9. They're going to color those yellow. And then they're going to use those objects to write the numerical sentence. In grade 3, here's an example. Addison got 40 points on yesterday's 10-question math quiz. Each question is worth 5 points, and there is no partial credit. How many questions did she miss? Again, thinking about the perseverance and making sense of the problem, helping the students to identify what critical information may be necessary and needed in the problem. Here's an example from 4th grade, where Tashika is placing 72 photographs in an album. She will put the same number of photos on each of 6 pages. She can put 4 pictures in each row. How many rows will be on each page? Again, thinking about organizing the information, how might you in your classroom with your students think about organizing this question in a way to help children model for them how to make sense of the problem? All right. Chart the information. Okay. Any other suggestions? Draw the picture. Model it out. Use cards or drawings. Use counters or cubes as a way to model the photographs. All right. show the picture like an array, suggest simpler numbers. All right, great. And then here in just the 5th grade, the same kind of problem as we work through. The ski team has a race in 3 hours, and it is 120 miles away. The team drives 50 miles an hour. Will they arrive at the race on time? Again, in this particular case, notice we're not asking for a numeric solution to the problem, but students have to think about what the question is asking and to see if it makes sense. Is there reasonableness to it as they work towards the solution? And so as we begin to think about the problems, it's helping students to make sense of the problem, not only recognizing that not always is it necessary to have a numerical answer, but the answer may be more of reasoning and discussion or description. As I move into the 2nd standard tonight, attending to precision, I have found that teachers ask that a lot. How do I help to encourage my students in the class to be precise? And I think it works to knowing your students, knowing what their limits are in terms of being able to persevere, to tolerate a little bit of a challenge, and how much challenge is good to move forward. And then when you know that the frustration is to a point where it becomes the distraction. But let's look for a moment at standard number 6, where we talk about attending to precision. Precision also includes the need for students to communicate precisely to others, to use clear definitions in their discussions and in describing their own reasoning. They have to be able to state the meanings of the symbols that they choose, including using the equal sign both consistently and appropriately. In dealing with precision, students need to be careful about specifying the units of measure or labeling perhaps the axes to clarify the correspondence with quantities in a problem. We know that they should calculate accurately and efficiently. They should express numerical answers with a degree of precision that's appropriate to their problem context and also for their grade level. In the elementary grades, for instance, students may give carefully formulated explanations to each other. And by the time they reach high school, they would have learned to examine claims and make explicit use of definitions. As students need to see the importance of those little things when they go about solving problems, because those little things can either make or break a solution. Students need to see the importance of using both the clear and concise definition, the appropriate symbols, the correct mathematical vocabulary, and the units of measure and labels. The details here then cannot be overlooked, for ignoring the details can result in equally incorrect answers or an incorrect solution strategy. Here's an example I thought we might work with for a moment, and I'm going to ask you again to pull in here with some comments when I ask some particular questions. In this particular case, you see on the screen the 10 digits from 0 to 9. And the question is can you use 4 different digits to make a fraction that is equal to 2? And as you begin to think of this problem, you probably recognize, well, there's several answers that may work for this. And so as we begin to be precise in our work, I might ask you, well, how would you know if you had all of the possible solutions? And so as we think about that, on the screen I placed one solution. It is 12, the digits 1 and 2, over 6, and using 0 as a placeholder for the tens place. So have I used 4 different digits? And does that fraction 12 over 6 equal 2? So does the solution meet the criteria of the problem? I would say yes. And then another example may be this, 78, the digits 7 and 8 over the digits 3 and 9 of 39. The 78 over 39 satisfied the conditions of the problem, using 4 different digits to make a fraction that is equal to 2. So before I ask, what all of the solution options are, let me ask you, what do you think the smallest numerator might be in this problem? And feel free to type in your solution or your answer. What do you think the smallest numerator could be to make this problem work? Remember, the conditions are 4 different digits. Could 10 in the numerator work? A 1 and a 0? What would have to be the digits in the denominator if 10 were the numerator? 0 and 5 if 10 were the numerator. Are we using different digits? The answer would be no. So the lowest numerator would be 12. Actually, 12 actually represents the lowest numerator in order to meet the conditions of the problem. All right? So let me just ask you then, I'll change this a little bit. What do you think the largest denominator could be in this problem and still satisfy the criteria of the problem using 4 different digits to make a fraction equal to 2? What do you think the largest denominator might be? 28? If 28 were the denominator, then what would be the numerator? 56? And so here again, helping students to persevere, to look through, to look for a strategy. It blends with the standard where we're asking students to look for regularity and patterns and repeated reasoning. We go to standard 7 and 8. We want students to persevere to see if they can come up with the most number that they have. Maybe creating an organized list is the model that we may have. And so as we think about that, if 6 is a denominator, what would the fraction be if 7 were the denominator? Or 8, or 9. Do those work? 12 over 6, 14 over 7, 16 over 8, 18 over 9. And then we might follow that same pattern by just counting upward. What if the denominator was 10? What would the numerator need to be? 20. Would we have 4 different digits? And the answer is no, because we used the 0 twice. The same happens when we use 11 and 12. The next group of numbers starts with 13. And as you see on the examples, the solution strategies on the board, we can work through, again, looking for a pattern and repeated reasoning, being precise and attending to the details of the problem. And as we work through the problem, we could actually just keep counting up and making an organized list. And so the solutions, and I've grouped these here in a way to group the denominators together in the families of 10. And so that the greatest denominator would be, as somebody mentioned, 48, with the numerator as being 96. And so the kind of problem provides an opportunity for students to work on calculations. The precision is important because it has to satisfy the criteria of the problem. It's an opportunity for students to work on their computation to become more efficient. It's part of the solving of problems that is the focus of the K-5 Common Core Standards, where students should be proficient in their computation. And so if you think about the kinds of problems, it's easy to change this as, could you make 4 different digits to make a fraction equal to 3 or 4 or 6? Whatever you'd like the objects to be, and it gives the students a chance to work on that. I actually use playing cards or number cards, so students can actually move the numbers around to create their models for them, for those students that need to see the tangible numbers in front of them as they work through this particular example. So as we think about number 6, where we're attending to precision, what I just want you to think about is how important it is to model, model, model for students. Modeling is the best way as teachers we can show students how to be successful mathematicians. And in our daily instruction, in our interactions with our students, be sure to use the appropriate and accurate mathematical vocabulary, helping them to develop the language of the mathematical experience. Students need to hear the accurate vocabulary frequently as it's used in the conversation for them to become comfortable enough with it to use it themselves. And also to be precise in your instruction. In working problems at the board or through the interactive whiteboard, or having students to come up to model. Set an example for attending to the details so that students understand the importance of it, the importance that details play in the mathematics. I'd like to share a first grade video for a moment of the first grade teacher and watch how she uses the precise language in the lesson, describing the vocabulary of the action that the students will work with in their processes.
Do you remember what kind of number sentence that is? 6 plus 6, what is that called? Jair? A double stacked, very good. Double stacked. When we add those two numbers, the same two numbers, add those together. Remember, those two numbers that we add together to get the sum, those two numbers are called the addends. We take those two numbers, 6 plus 6, those are those doubles, they're called addends to get the sum, the answer for an addition sentence. Take a look at number 3. Number 3, let's read through, follow along please. The clown sells toys in boxes of 2, 4, and 6. Noah's mom buys 2 boxes with 10 toys in all. Which 2 boxes does she buy? So what were you thinking? What did you have to do? You had to figure out which numbers to use, right? You had to figure out, do I use 2, 4, 6? Which ones do I use? But I had to get a total of 10. So what did you do? Zola, what did you guys think of?
We were like adding like the same numbers as the paper said, but Haley said let's add 4, and we did. And it was a total of 10.
So you wanted to start off and you guys wanted to add all 3 numbers. You wanted to add 2, 4, and 6. But you knew you had to get a total of 10. So Haley helped you, and Haley said to do what?
Add 4 because it is a total of 10.
4 and what?
4 plus 6.
4 plus 6. Did everybody add 4 plus 6 to make 10?
Yeah.
Thumbs up? Good. So down below, we used the numbers 4 and 6 to make 10. I'm going to use 4 red cubes and 6 blue cubes. Use your cubes, please. 4 plus 6 equals 10. Good. Nice job, Anthony. Very good.
What is interesting in the example there is that you probably noticed when little Zola said we had 4 to get 10, the teacher didn't let her off the hook by making the assumption that she knew she was adding 4 to a quantity of 6 because Zola hadn't expressed that quantity of 6 yet. And that the teacher, through prompting and questioning, made Zola go back to make sure that she was precise in articulating where the 10 came from, what was being added to the 4 in order to get to the 10. And that's a good strategy to work as we're working in on this standard to help students recognize it's not okay to take the shortcut if we're not going to be precise in both how we describe and in the language we use. So think about that as you, in the classroom, model both the precise and the accurate use of the mathematics vocabulary and language. And then think about how this teacher encouraged the students to use that precision in the language and model and think about that in your own classroom experience. Here I'll just share with you for a moment again a fourth grade example of the same type of opportunity where the teacher models
Math
with
coach
her
and
students.
author Robin Silby discussed the importance of precision in mathematics at the upper elementary level. Let's watch as this fourth grade class uses precise mathematical thinking and language.
I want you to look at problem number 11. Problem number 11 says, Leah used blocks to build model towers. The table shows how many blocks she needs for different sized towers. How many blocks will she need to build a 7-foot tower? Find the pattern, talk it out, try and find the rule, and find the missing number. Talk it out amongst yourself. Think out loud. Okay, I want you to talk about how did you know it was 32? What did you do? Did you do the reverse operation? So you added, you can take 160 minus 128. Talk about that. Write it in your book.
I think I did it.
We'll stop and write the numbers here so that we can see it. Dominique, just explain how you got yours.
I took 160, I subtracted it by 128, I got 32, and then I took 192 and added with 32, and I got 224.
So each one of you are going to say your numbers and then tell them what your rule is, okay?
My rule is add 100 3 times and subtract 100 2. So 0, 100, 200, 300, 200, 100, 200, 300, 200, 100, 200, 300. My rule is add 3 and subtract 2. And my numbers are 1, 4, 2, 5, 3, 6, and 4.
The example in the end that the teacher was working on was having the students make input-output tables, basically, in which they were creating rules and then showing the pattern within the computation of the rules that they were working on. In both cases, I think what you'll find is that how the teacher specifically encouraged the students to speak precisely, and that how did the students themselves demonstrate that precision in their explanations as they were talking through how they solved the problem. And again, I'll just take a few moments to share with you a couple of examples from grades 3, 4, and 5 in the McGraw-Hill My Math program where these standards are modeled. For instance, in this particular case, again, it's not about a computation example where it's a numeric expression, but it's more about how students use the vocabulary and the language in order to develop the answer. And the question here is building on the chapter essential question, how can an array help you solve a related multiplication and division problem? In which the focus on developing the vocabulary is very important. Here in grade 4, the question is about Clarissa having 4 pictures that are the size of the one shown, and then what would the perimeter be of the rectangle formed if 4 pictures were laid end to end? Having students talk through and use the My Workspace as a way of helping them to model the process they would use. And here at grade 5, on a Friday, the museum had 185 visitors. On Saturday, there were twice as many visitors as Friday. And on Sunday, there were 50 fewer people visited than on Saturday. How many people visited the museum during these 3 days? Again, attending to the focus on the vocabulary is important in helping the students to begin to think about how they're going to solve the problem, looking for the entry point to the strategy that they'll use towards the solution, and then being able to describe in articulate and precise language how they arrived at that solution. So what I'd like to do is just summarize for tonight, and I appreciate your time with me, is that as we look at these 2 standards, standards 1 and 6, they are really those habits that are hard to instill in students but take time over years to develop, and that is to be precise in their calculations, to work to a level of perseverance in which we provide opportunities to challenge students and recognize what levels they get frustrated at. Helping students to attend to the details, and that is again about being precise in both the use of the computation, but also in the vocabulary. And the development of the vocabulary is essential to help students understand the meaning of the mathematical terms. So I want to thank you this evening for your participation. I've enjoyed this workshop series on the 8 mathematical practices. If you would like to see our other sessions, again, you may go to mheonline.com/mhexchange. I'm Michael Comer from McGraw-Hill. I want to thank you again for sharing your time this evening on the mathematical practices. Thanks a lot and have a great evening.